so we have some more distance time graph notes. These are really going to help you really understand the difference between these types of graphs and how to kind of read them. So it's really good stuff. If you want to take notes, feel free. The PowerPoint is going to be under the Files tab with speed distance time graphs, okay? We need to match the graph to the correct scenario first. So that's the first thing we're going to do. Let's look down here at scenario number 1. So it says a motorbike travels away from home at a steady speed. So if you remember when we talked about this yesterday, steady speed, you're looking for a smooth diagonal line. So we don't want it to be horizontal and we don't want it to have any whoops in it. We just want a smooth diagonal line. So if we look, that's the one right there. See that smooth diagonal line? So this matches this scenario right there. So I'm going to put a C underneath there, okay? Well, let's look at scenario number 2. So this says a car remains parked at a car park. Makes sense, right? So if a car remains parked, does that mean it's moving or is it standing still? That's right, it's standing still. If cars are parked, it means it's not moving. On these distance time graphs, when we're looking for one that's standing still, what are we looking for? We're looking for that horizontal line, right? We're looking for a line that looks just like the horizon outside, that horizontal line. Which one of these is a horizontal line? That's right, this one right here. So here, we've got a line that just goes side to side. It's not going up, it's not going down, it's not curving. We're just standing still right here. So this one matches right there. So I'm going to put A, because this scenario matches this one. Now, process of elimination, we know that the one in the middle is going to match this one right here, but we're still going to talk about it because there's some good stuff in there, okay? So here we have a runner runs at a steady pace to the end of a track. He then turns around and runs at the same speed back. So he runs at the same speed and he goes home, okay? So when we talked yesterday, we talked about the constant speed, okay? It's going to be at a diagonal. And then going home, that constant speed, that nice diagonal, is going to go the other direction. So when you're going from home, you're going away from home. Your distance is getting greater. Well, when you're coming back home, your distance is going to get smaller. So that means you're going to be going down, down, down the graph, okay? So because here your numbers go 0, 1, 2, 3, 4, 5, 6, 7. They got 6 steps away, and then they turned around and went 5, 4, 3, 2, 1, and then back to where they started from, okay? So they went away, and then they come back home. So this graph matches this one right here, so I'm going to put a B right there. Does that kind of help understand these a little bit? I know it seems a little bit crazy, a little bit complicated, but it's really kind of cool, okay? Let's look at the next one. Okay, good deal. All right, here we have question 1. Which graph shows the object traveling at a faster speed? So yesterday we talked a little bit about this. The closer to horizontal, remember standing still is a horizontal line. So the closer to horizontal a graph is, a line on a graph is, the closer to stopped it is. And the closer you are to stopped means the slower you're moving, okay? So we can just glance right here at these two graphs and figure out one of these is going slower than the other one because that line is way closer to horizontal, okay? Which one of these do you think it is? We've got A and we've got B. If you said A, you're exactly right. This graph is way closer to horizontal than this one right here. So the correct answer here is A. Okay? Now if we wanted to get crazy, we could actually figure out the speed on these two graphs. Let's look and see how. We've already talked about the speed formula. We talked about that for days. That is speed equals distance divided by time. Okay, so we're just going to pick a spot right here. We'll go at 3 seconds. We'll go up. Well, maybe not 3. Let's do right here at the end. That's 5 seconds, okay? So 5 seconds, that's a pretty good even number. So here we've got 5 seconds, and our distance is going to be 40, and we see this M right here for meters, right? Okay, so we need speed equals distance divided by time. Here's a spot for our distance. There's a spot for our time. What's our distance again? Well, distance is the up and down. It's on the y-axis. And we've got 40 meters. So I'm going to put 40 and an M for meter. Okay? Next we need time, right? Well, we've got our time right here. We've got 5 seconds. So I'm going to say 5 and an S for seconds. Well, if we do the math on that, I bet you can do it in your head. What is 40 divided by 5? If you said 8, you're exactly right. So S equals 8, and then we need to bring our units down, remember? So meters per second. So the speed on this graph right here is 8 meters per second, okay? And now we can pick any spot we want to on this graph right here and do the same thing. Well, let's do 5 seconds again. And there's our distance at 5 seconds, okay? So we've got the same distance, we've got the same time, different distance, I'm sorry. Same time, different distance. S equals distance divided by time again, okay? We know that, we've been talking about that for days. So here's a spot for our distance and a spot for our time. What are we gonna write for our distance? Well, if we look at this graph right here, that says 100. And then we've got an M for meters right here. So we're going to put 100 M for meter, and then now we need our time. Well, we'll look right down here. Here's our time, and that says 5 seconds, okay? So we're going to put 5 and then S for seconds. Now, like I said over and over and over again, you can totally use a calculator if you want to, but you don't have to, because I bet you can do the math on this without one, but it's okay if you can't. So S equals 20. We need some units over here. Meters per second. There's our speed for this graph. So here we've got our speed is 8 meters per second. Here our speed is 20 meters per second. And we've done the math. Now all we would have to do is say which one of these numbers is bigger, because the bigger that number for speed, the faster you're going to go, right? So that was kind of hard last year for some of my kids to kind of grab. So if you think about it, right out here in front of school, our speed limit is 35 miles an hour, okay? You gotta go super slow, be really safe in case kids are walking around, okay? So 35 miles per hour right out here in front of school. Well, if we get on I-30, the speed limit is way different. It's 75 miles an hour, okay? So which speed is faster? 35 right out here in front of school, or on the highway where it's 75? Well, 75 is faster. 75 miles an hour is way faster than 35 miles an hour, okay? And the way we know that is because it's a greater number. It's bigger than. So the same thing right here. We've got 8 meters per second. We've got 20 meters per second. 20 is greater than 8. So this graph, where they're moving 20 meters per second, they're moving faster right here, okay? So which graph shows the object traveling at a faster speed? Well, this one right here. Well, now we know 2 different ways that we can get that information off of these graphs. We can just look at it, know the one that's closer to the horizon, horizontal, is going to be moving slower. The one closer to up and down, they're going to be moving faster. Or if you want, now you know that you can actually figure out the speed by looking at a distance time graph. All kinds of crazy cool stuff happening here, right? Okay, let's see what happens next. here we go. This graph is doing some different things. You can see we got kind of a good angle right here, and then we go right to horizontal, and then we're kind of going up at a lower angle right there, okay? The question says, which part of the graph shows that the object is stationary? So that's just another way to say at rest, or stopped, or not moving. So if something is stationary, it just means it's not moving, okay? So, just like what we've talked about, which part of this graph looks like something is sitting still? It's not moving, it's at rest. Is it A, look like it's at rest? So we've got a nice diagonal line, okay. Is that at rest? No, that's not at rest, right? That diagonal line right there says that it's at a constant speed, so that can't be it. Well, let's look at C over here. This line is closer to horizontal than this one right here, right? But it's still a diagonal line that's kind of going up a little bit. So that's not it either, because we know that they're moving right there. But B, now B, that's a straight horizontal line right there. There's nobody moving on that horizontal line, because we know a horizontal line on a distance time graph means that you're at rest. Man, it's kind of cool. I love distance time graphs. Okay, y'all are doing great. Let's see what we've got next. So, I'm going to pause this video because I've got to go out in the hallway and make sure nobody gets in any trouble out there. But we'll be right back.